Hello and welcome to the next video. We're continuing with forces, and what we're going to be looking at this time is Newton's third law. We might remember what this one is, but this is one that deals with paired forces. So it's for every action there's an equal but opposite reaction. Basically we can think of this as being like forces always occur in pairs as they need something to push against. When you push down on the floor to walk, the floor is pushing back on you to make you move. It leads to some fun examples. You've probably all seen GIFs like this of folk getting recoil from guns. When you fire the gun, there's a huge force put on the bullet to fire it forward, and then that bullet puts the same force back on the gun, and which, if you're not expecting it, can lead to things like that. I'm sure these are probably exaggerated a bit, but you get the idea. There's other real-life applications of it you might be more familiar with. If you're getting off a boat onto a pier or a jetty or just onto the beach, as you step off the boat, you're putting a force down on it to step on it, and that's pushing you forward, but it's also going to push the boat backwards and away from you. Or another fun example, you've got big inflatable things like this. If someone jumps onto that, they're putting a huge force down onto the inflatable when they jump on it, and then that huge inflatable puts the same force back on anyone who's already on it and flings them up in the air. So let's look at it in a bit more detail and see what's actually sort of happening and what we call these forces. So we're all producing a force right now. I'm sat on my chair recording this, you're probably sat down watching it, and you're putting a force on that chair, aren't you? So then why aren't you moving? Because we've already said that forces create movement. So here you are looking all smart, enjoying your home learning, and you're putting a force down on the chair. Now, it's not really important for just what we're talking about now, but that force you're putting down on your chair, that's weight. That's because of gravity, that force you're putting downwards. So that will come back into it later, just to highlight it now. So we would then have an unbalanced force acting downwards, because there's nothing pulling us up. So therefore we should be accelerating downwards. But what actually happens is the chair provides an equal and opposite force to us. So it provides an equal and exactly opposite and exactly equal, so that we don't move at all up or down, we just stay where we are. And so this force it puts in opposition, opposite to us, we call that the normal force. So that's the force something puts opposing another object, like the equal opposite force. Now, let's look at how we can actually use this knowledge in a question, because we're at the point now where we have to take into account these equal and opposite forces when working things out. So what we're going to have here is a fairly standard, actually, exam type question. So we say a rocket taken off from Earth has a mass of 4.5 times 10 to the 3 kilos, and the engine force applied is 1 times 10 to the 5 newtons. When it's split up, it wants us to first work out the resultant force. That just means the net, the unbalanced force. Then second, the acceleration, then the speed after 5 seconds, and then the height the rocket has reached in 5 seconds. And I say this is quite a standard question because each of these parts builds on the part before it. So we need the answer to part A to work out B, and we need the answer to part B to work out C and D. That's quite often how these big questions are split up in the exam. So first, let's look at A then to work out the resultant force. Let's think what's actually happening. We've got our rocket. It's got a force going upwards because it's taking off. And it's telling us that force going upwards, well, we know that's coming from the engine. That's what's pushing it upwards. But we know it's got to have a force going down as well, doesn't it? Just like us sitting in the chair or anything on Earth has got a force pulling it down. And that force pulling it down is its weight. So its overall, its resultant force is going to be the difference between these, is going to be what's left over when you take away the weight. So let's start then with working out that weight. We should hopefully know by now, the formula for weight is W equals mg, mass times gravity. So we know the mass, we know gravity, we're assuming this is on Earth. Well, it says it's on Earth actually, so we don't need to assume. And so we just sub those in, W equals mg, so mass times gravity, that gives us a weight of 44,100. So there is a force coming down the way of 44,100, and it's already told us that there is a force going up the way of 45,000. So to work out the resultant force, we're going to have to do that 45, I've been silly, it's not 45,000 going upwards, it is 100,000. Anyone can make a mistake, there you go. It's 100,000 going upwards. And so, to work out the resultant one, we take that 100,000, we take away the weight, because that's acting against it, and that gives us that the resultant force is 55,900 newtons going up, and that's what makes the rocket take off. So, let's look at the next bit now. Let's look at part B, which asked us for the acceleration. So, it's asking us for acceleration. We know the force now. We know the force it's moving with is 55,900. See how we're using that from the last question. And we know its mass. So we're going to use our F equals ma equation here, but we've rearranged it to work out the acceleration. So this is just your F equals ma equation, but we've rearranged it to work out the acceleration. Substitute in. And that gives us the acceleration is 12.4 meters per second squared. Then part C, that asked us to work out how fast the rocket was going after 5 seconds. So again, we'll write down everything we have for that. So we know its acceleration now. See how again we're using something we worked out in another part. So we know that acceleration. We don't know V. V is the final speed we're trying to work out. We know U, we know the starting speed was 0, so it started at rest, and we know the time is 5 seconds. So we're going to use our A equals V minus U over T equation. But again, we're going to need to rearrange this to find out V. So you see how this stuff we're doing now is bringing together everything we've been doing before and putting it all together and showing how it's all linked. So if we rearrange that, that gives us V equals U plus AT. Substitute in, we get the velocity is 62 meters per second. And then finally, part D asks us to work out how high the rocket got in that time. So we can't use our normal distance equals speed times time formula. And the reason we can't use that is because the rocket is accelerating, so its speed isn't constant. So this is going to come back and use what we did a couple of videos ago, and that's to do with velocity time graphs. If you want to work out the distance traveled when something was accelerating, you have to plot a velocity time graph of it and work out the area underneath it. So if we do that, that's going to look like this, because it starts at a speed of 0 down here, and by the end it's at a speed of 62, because that was the final speed we worked out that it got to. Then it does this over 5 seconds. So if we have a graph like this, the area underneath it is the distance travelled. So the area of that triangle is a half times the base times the height. It's a half times 5 times 62 gives us 155 meters. So that question then has used everything we've done so far about acceleration, everything we know about forces and weight, what we know about velocity time graphs, and put that all together to work out what's happening in the initial stages of a rocket takeoff. So it's all linked, everything we've been doing. Now, the idea of especially an example like a rocket or something in the air of these balanced forces leads us to quite an important concept in physics, which is terminal velocity. You might be asked to explain this, and so you need to understand what's happening. So, terminal velocity is to do with objects falling. So, when something is free falling towards Earth, like a parachuter who's not yet let out their parachute or anything like that. They've got two forces acting on them. They've got their weight going downwards, gravity is pulling them towards the Earth, but they've also got air resistance pushing against them, pushing back up the way. So at the beginning, their weight is greater than their air resistance, so they accelerate towards the Earth. But the faster you go, the bigger the air resistance gets. So the reason air resistance gets greater as you go faster is because air resistance is just friction. It's just friction between you and the particles of the air. So the faster you're going, the more you're pushing against those particles, the more friction is created. And so, since air resistance gets greater the faster you go, you eventually reach a point where the air resistance matches the weight and they balance out. And so because the forces then are balanced out, remember balanced forces means something is either not moving or moving at a constant speed. So you stopped accelerating. You're moving at what we call the terminal velocity, the maximum speed you could get to. Now, this whole thing, terminal velocity, and the last rocket question we looked at, is all because of basically these two equations and the ideas of gravity and acceleration. So we know these two formulas. We know the unbalanced force is equal to the mass times the acceleration. And we know that weight is equal to mass times gravity. But remember, weight is just a force. These two formula are exactly the same thing because weight is just a force. And what this means is the g here in this equation, that is just the acceleration because of gravity. So if you dropped a stone on the Earth, it would accelerate at 9.8 meters per second squared because that's what gravity is. And so that means an actual other definition is that the gravitational field strength on the planet, the strength of the gravity, is the force per unit mass. So in other words, a really important bit here to remember is this statement here in the middle. If you drop something on the Earth, its acceleration is 9.8 because its acceleration is just gravity. So that's the really important point for here. So that's all we're going to cover with these forces things. Then we're going to move on to some other types of motion. So hopefully that was all understandable in this video. And if not, you know how to get in touch with me. So thank you for watching.